Okay, for the next session, it's my pleasure to introduce Federico and Sebastian from Red Hat. They're going to discuss about Rook, Ceph, and ARM.
Hi, I'm Federico Lucifredi, Product Management Director for 16 or 17 Red Hat Ceph storage releases. I kind of lost count. And I'm joined by my colleague.
Yeah, I'm Sebastian. I'm a Ceph engineer. I work for Red Hat, and I'm one of the maintainers of the Rook Ceph piece in Rook.
So welcome to the Caffeinated tutorial. We have 40 slides and a demo, and we need to get going. So fasten your seatbelts. Let's start from basics. For those of you who do not know, Ceph is an open source distributed software-defined storage solution that allows users to access data through different interfaces, including object, block, and file. Or, as we like to think of it, Ceph is the Linux of storage. Not just because of the open source aspect, but because there are many, many technically fascinating things to Ceph's beautiful and immensely scalable design that I'm not going to cover here. I will just say that in storage, we like to say that things are never exciting, except when storage doesn't work. That is actually not true of Ceph. Ceph is interesting and exciting on a technical level. And that is why we allow ourselves to show some chutzpah and call it the future of storage. Some basic terminology. Ceph has a multitude of daemons. The ones managing actual storage are called OSDs, which also manage data replication and resiliency, among other things. This is the Rados layer of this diagram. Higher level interfaces provide block storage, the RBD library here, or object storage in the form of the RGW daemon, which delivers the AWS S3 protocol. On top of the underlying storage core, one of the things that is fascinating about Ceph is its data placement approach, requiring no gateways but finding data algorithmically. In short, if you know how distributed hash tables work, you already know what concept Ceph is built around, and what makes it look more like a peer-to-peer networking system than traditional storage. The important thing you need to understand here is that Ceph delivers storage out of commodity servers, scales out, potentially without limit, and today to tens of petabytes per cluster, and delivers the 3 storage interfaces out of this distributed system of individual nodes, which look more like your compute servers than your traditional storage. So, why is storage in Kubernetes hard? Well, let's cut to the chase, and let's say that as microservices are decoupling infrastructure and application logic, developers no longer need to worry about infrastructure. That is great for developers, but the operators still need to figure out how to make things work, even if it's behind the scenes. The Kubernetes architecture is a very dynamic environment with containers being created and destroyed based on healing and need and load. But the key issue here is that local persistent storage cannot support this dynamic behavior. Data locality gets in the way. Kubernetes is extremely powerful in many regards, like scalability and management, but it did not originally support storing state all that well, to be honest. Essentially, its architecture badly wants to be an ephemeral storage environment. Statelessness is close to the heart of the pets and cattle metaphor that we like to use for clouds. But many, if not most, of the useful applications today are stateful, and that brings the need for external networked storage. The simplest solution to this problem is to have apps running inside the cluster with their storage residing in an external storage setup, such as a public cloud, or worse yet, the legacy storage appliance that you already have in your data center. Using a traditional storage appliance usually kills the scalability that you won on the compute side by building a cloud and cripples its economics. But this is not simply about bashing the limits of appliances. Even if you're using a uniformly scalable software-defined storage provider like Ceph instead of an appliance, you have this picture of storage as something that exists outside of your cloud, cloud fabric, usually underneath it. Notably, this is how OpenStack does storage. And there are some well-known limitations with this approach. The most notable one here is that it's not portable. If you're relying on external storage, you need to have it already accessible as you are deploying your cluster, because it is not built in Kubernetes. And when you want to move your application to a different cloud provider, migrating between Amazon, Microsoft, and Google, which is realistically all your options, or even moving between public clouds and on-premise, you need to worry about how that external storage is going to go there with you. Another thing to consider is that if you're relying on a cloud provider, you may want to avoid the vendor lock-in coming from their specific storage implementation. So one approach to solve this problem is to run storage on top of Kubernetes rather than underneath it. As modern software-defined storage like Ceph is homogeneous with compute in that it uses servers from your favorite iron vendor of choice as building blocks, this is relatively easy to pull off. You can YAML your way to success by deploying our storage as just another Kubernetes application. Maybe a special one, but not that special. So that is building block one. Here's the next bit. Another aspect we need to discuss before we tackle Rook is how Kubernetes interfaces with storage. In other words, drivers. Storage in Kubernetes has multiple abstraction layers, ultimately intended to deliver workload portability. At its most basic, the storage interface in Kubernetes pairs storage volumes to requests coming from pods. In the most sensible of these variations, using a remote network-based storage system like Ceph delivers dynamically allocated persistent volumes to claims made by pods. This is done in a way that is decoupled from the local implementation while requiring no knowledge of the local platform by the user. The administrator can still and probably should still have local knowledge. This allows a workload to move from, let's say, GKE to Amazon. And we're not going to go over all of the details of the storage implementation in Kubernetes, but others have done that work for us. Saad Ali of Google has a very nice talk that is easy to find on YouTube, covering the fundamentals of PVs and claims and how they interface with each other. And the IBM FSS FCI team also has a series of short videos detailing that in painstaking detail. So looking at a slightly higher level, the first set of Kubernetes volume drivers were so-called in-tree drivers, maintained as part of the Kubernetes code base itself. And here is how the in-tree drivers connect to remote storage. This approach enabled more rapid development of Kubernetes itself, as it did not require a consistent storage API to be developed. In-tree plugins enabled dynamic provisioning of user volumes. Volume drivers conveniently attach pods to storage automatically, regardless of which nodes are actually hosting the pods, all the while providing sufficient abstraction to enable this workload portability that we're going after. On the other hand, in-tree plugins can be painful for the Kubernetes community to maintain, and any bug in the plugin code could affect Kubernetes core components. Security-wise, these in-tree drivers also have the same level of access as Kubernetes core components, which is less than ideal. Maintaining plugins in-tree can also be painful for vendors, as they have to keep up with Kubernetes fast release tempo, may have to backward fixes, and not that I'm complaining here, they may have to open source their code. Of course, the remote storage in this picture could be AWS EBS, Google Cloud PD, or anything else that has an in-tree driver, but obviously in this session we like Ceph, so the example is Ceph-based. In the new world enabled by the container storage interface, volume plugins are maintained out of tree. Well, this requires the well-defined API that we dodged earlier and couples API changes with Kubernetes releases. It has an amazing feature for operations. Storage can once again be treated as a workload to be containerized and deployed on Kubernetes cluster just like any other. So first we talked about doing it with the storage itself. Now we can actually do it also with the storage drivers. Storage plugins can now be provisioned simply by calling kubectl with a YAML file. The Kubernetes team and third-party vendors are responsible for separate discrete components, and security access does not exceed the permissions that are actually required for the task. These components run in sidecar containers, sharing network and storage access with the main workload container. You can see here from the mess of arrows that clearly there is an API at play, but we don't really need to understand all that unless we're writing a driver. The bit that is interesting to understand, however, is that all this abstraction is not changing the performance from the previous picture, because once the storage is attached to a pod, the interface is direct. There is no intermediation of the data exchange. So maybe allocating the storage looks a little bit more complicated, but performance-wise, it's exactly the same thing. Some more details on implementation here. Probably too much detail, frankly. But one bit of driver lore worth knowing beyond what I just mentioned, and something that is not on the slide, is that there are these things called flex volume drivers, which are popular with Rook, so they are worth mentioning. Flex volume drivers are another out-of-tree effort, which is still maintained by now, but now considered already legacy and not really being enhanced. The flex volume drivers make exact calls to a file on the local machine. Operationally, this may be limiting, as you need special access to deploy these files. So what I was just saying about CSI, that you can deploy the drivers as a YAML, is not really true of flex drivers unless you have special access, which actually is not possible in certain public cloud environments, notably Google Cloud. As a result, they are not as easy to deploy as the newer CSI drivers and are kind of falling out of favor despite being still maintained. The current effort is going fully into the CSI API, and that's where you should see things going as things move forward. The Ceph CSI API combines in one interface the best of the Kubernetes volume system and the CSI interface, providing dynamic provisioning of Ceph volumes and automatically attaching them to workloads. Use of the Ceph RBD driver here results in transparency and provisioning, by the way, as well as all of Ceph's infinitely powerful storage architecture is hidden behind the covers here. So you get very powerful storage, but you don't necessarily know how it's doing its magic, which for many users is actually a good thing. The integration here was completed with Rook 1.0. And as the user does not need to be privy to Ceph's internal implementation detail, an application could move from your private data center to a public cloud without adjustments, provided you manage that pesky data gravity aspect on your own. By the way, volume claims in Kubernetes have access modes, which are known as RWO, ROX, and RWX. That's another interesting detail about drivers. RWO and RWX are the most popular choices. RWX is used to share data between a pod's multiple containers. RWO is the default choice, providing storage in exclusive access to one. In Ceph, RWO is delivered by RBD to ensure maximum performance, while Ceph-FS delivers the shared RWX mode when it's required. And now we're finally reaching what we are all here to talk about, which is Project Rook. Rook is the CNCF storage operator of choice. And as of today, its most solid integration is with storage as delivered by Ceph. A Kubernetes operator functions by letting the site administrator define a target state and then working its way toward achieving and maintaining that state for a Kubernetes hosted workload. It doesn't do it in a vacuum. Rook does just that for Ceph storage. As soon as Rook is deployed in a Kubernetes cluster, a complete Ceph environment is running. And while one might be forgiven for thinking that Ceph has long solved the issue of persistent resilient and remote storage, that is not really what Rook does. Rook manages the operation of the Ceph cluster in the Kubernetes environment so that the operator is isolated from having to do a lot of chores, him or herself. Rook's approach to hiding complexity from the user couples uniquely well with Ceph's open, massively scalable software-defined storage system, delivering a flexible, scale-out architecture on clustered commodity hardware. Ceph brings a vibrant open source community and its own thriving vendor ecosystem to the combination of the two projects. Ceph's advanced storage technology pairs with Rook's high usability to deliver what is a perfect combination for developers and operators hosting workloads in a Kubernetes environment. And on that note, I will hand over to my colleague, Sebastian Hahn, to dive deeper into the architecture. And I think that we need the other microphone on, please.
All right, thanks. Quick question before I start. How many of you knew Ceph before Rook? And how many got to know Ceph with Rook? Okay, just a few more. So it's good that I was actually thinking that we will have to do more introduction of Ceph, but actually the audience is actually really familiar with Ceph, so it is actually a really good thing. So we have two big themes, right? The first one is installing Ceph as part of a Kubernetes cluster. So in this scenario, Rook is actually responsible for installing, configuring, scaling, upgrading Ceph, and managing its entire lifecycle, just like an application running on Kubernetes. That's the first part. The second one is actually providing persistent storage to applications, and this is done via CSI. So Rook not only deploys Ceph as an application in Kubernetes, but also helps you using that storage for your applications. So the Rook operator actually implements the operator pattern. It's actually a really popular concept in the Kubernetes world. Basically, an operator is just an entity that runs in Kubernetes so that it will extend Kubernetes knowledge landscape. So if Kubernetes doesn't know something, then via an operator, then we will be able to instruct Kubernetes that you know how to deploy a Ceph cluster, you know many more things. And all of those things are being done via CRDs, so custom resource definitions. What's really important to understand is that from a user perspective, the user always has to inject what we call a CR. So basically the CR is the instantiation of that CRD, and we're going to go through an example of a CR in a minute, but what's really important to understand is that Rook, with the help of Kubernetes, will always make sure that the desired state that was provided by the user will always be maintained throughout the lifecycle of the cluster. And basically what Rook does is three main things, right? It's observing changes that might happen to that CR or in Ceph, and will react upon those events. So basically observes, analyzes, and acts any changes that might come up on the platform itself, or just because the user decided that they wanted to maybe expand the cluster or just add more things to it, like more monitors, for example. So now that you're familiar with Ceph, Kubernetes storage in Kubernetes, and Rook more generally, we're going to dive into Rook's architecture a little bit more. So what you see at the very bottom here, and I'm going to use these, what we see at the very bottom are, and this is again theme number 1 and theme number 2, right? So theme number 1 again is deploying Ceph as an application in Kubernetes. So OSDs are object storage daemons responsible for basically replicating objects, writing objects, scrubbing objects. We have mons, basically the brain of the cluster. They come with 3 or 4, it's just or 5, sorry. It's always an even number, an odd number, sorry. They maintain the map of the cluster, but not in the data path. And then we have other daemons like MDS, Rados Gateway, and MGR. So the MDS is basically the metadata server that exposes the distributed file system of Ceph, where Rados Gateway is the REST endpoint where you can consume data at rest. The manager is just a pluggable interface that you can use to extend Ceph capabilities. So like it's a pluggable mechanism where you can add more, you can add things like metrics and so forth. On the second theme here, we have so obviously the Rook operator, the main thing responsible for all the things we do, so the bootstrap, the maintenance of Ceph, and the connection. So the connection is actually being done by agents here, so we call them agents. It's actually really generic, but agents in this case actually represent CSI. So at the very top here, we have your app and the claim of your volume. So as a user, you just claim for volume. We do dynamic provisioning, and then these agents are basically running where your app run, and they will just map the storage and provide it to your containers. So going back to this desired state that I was mentioning earlier, so this is a really simple example of a CR that you will inject into Kubernetes so that you can deploy a Ceph cluster. And what's actually really interesting, as you can see, is that within 20 lines of YAMLs, then you can actually get a cluster up and running. So that's actually, in terms of user experience, that's actually really good. So if we look a little bit, so we have the namespace, but we don't care much about this at this point. So if you look quickly at the spec, what we can see is that we only have to provide a relatively few information here. So we have the image, which is actually critical because it basically states what Ceph version we want to use. So these images are provided by the Docker. Well, we provide them as the Ceph team. They're available on the Docker Hub. And what's really important about that is that these images are built every day. So whether there is a new Ceph version or just a change on the base OS, then we will always build a new image out of that. So we make sure that we don't have all the potential vulnerabilities in that image will be solved because we just provided a new one. These images should be the ones that you use if you're looking at deploying Ceph in containerized environment, because these are, let's say, golden side images provided and maintained by the Ceph team. The mon count is just it's actually something that I would like to add, because if you're looking at deploying Ceph, you want it to be really easy, so you wouldn't really have to choose how many months you want to run. We should be able to tell you that. And I really hope in the future that we can remove that flag, so you don't actually even have to think about how many months you want to run. We can obviously ask you as well if you want to take advantage of the Ceph dashboard so that you can visualize and interact with the cluster to see what's happening. And the very bottom is actually potentially the most important one. It's related to storage, right? So we have different modes, different capabilities here. That's actually the simplest one. So you can specify, you can say use all the nodes and use all the drives. So we will go and scan all the devices on every node that are available in your Kubernetes cluster, use the drives and add them in Ceph. That's the easiest scenario, I would say. We can be more granular and more specific here, so you can specify nodes with a particular label that are actually maybe labeled like storage nodes, and then we will go through these nodes and again scan the drives and detect which drives are good candidates to become actually storage daemons, and then add them to the cluster. You can go even deeper here by specifying which node and which drives you want to use as storage backend, storage OSDs. Sorry. So these are the custom resources. The CRDs are available. They are actually being provided by Rook. So we already discussed the first one, because that's actually just deploying a Ceph cluster. Well, not just quite deploying a Ceph cluster. The second one is the block pool, which basically a pool in Ceph is just just a storage entity where you will be storing your data. Pools can have different capabilities. Pools can be attached to a certain portion of your infrastructure if you have different types of workloads. So you can be assigning, let's say, one pool for object workloads or one pool for block workloads. And these workloads are obviously really different. And I mean, in terms of I/O, they're more intensive than others. So you can have dedicated hardware for this. So this will actually be creating a pool again, with different capabilities. You can use as a storage class, and then once the user wants to claim a PVC, then they would just use it. Same goes for the file system here. We can deploy the MDS, so the portion of the distributed file system of Ceph. We have Ceph NFS as well, which actually relies on Ganesha under the hood. And Ganesha is actually using the Ceph metadata file system to expose NFS shares. Ceph Object Store and Ceph Object Store and Ceph Object Store user are actually pretty simple, right? They just bootstrap Rudder's gateway instances so that you can consume a REST API endpoint similar to not similar to, it's just like an S3 endpoint. So if you're looking at developing on S3, then you can bootstrap those and then you're ready to go. Okay, so that's the embarrassing moment of this talk because we actually had something working yesterday, and like a couple of hours ago, everything started crashing. So I'm just going to let Federico explain what actually happened. Yeah.
So the demo gods are not smiling on us today. Let's put it that way. Let me see, can I bring up the terminal? I want to grab the terminal. Yeah. Oh, it's the other side. Oh, sorry, that's right. But it's not doing it. It's the bottom.
Okay, I guess we're just trying to show you a screenshot.
I was trying to show you what we have running, but it's not going to the right desktop.
Okay, let's just switch back to the presentation.
Yeah. Completely going wrong. Okay, now it will go right. Where is the cursor? Here. There we go. So, at least the terminal is obeying. So, we have a bit of the details of the cluster construction in the slides, so at least we can tell you what the cluster looks like. But I wanted to show you what we actually had running. So this was validated last night around 11 hours ago, and then 3 hours ago when we were doing the final rehearsal, the master stopped answering us. What is going on is actually not at Kubernetes level. It's typical embedded development problems. So we have to get U-boot running. If you're familiar with that, that's the typical embedded bootloader. The kernel, obviously, and the user land, and then get Kubernetes on top. The higher we get in the stack, the easier it is. So in effect, with Rook, we didn't encounter any significant problems, and Kubernetes was fairly straightforward as well. The part that we are seeing instability with is that we're getting some kernel panics because we had to do some kernel rebuilds to add the RBD module to the image that we're using for the system. And there is something obviously wrong in our detailed configuration because we're seeing some inconsistent behavior in terms of memory access. So in terms of when things are running, you actually get to do get pods fairly normally, and you see the pods that would come from a Rook cluster. But then it seems to have a significantly high probability of killing itself within a certain number of hours because of these random kernel issues. And the way they are happening, they corrupt the file system. That's a short part. The plan is to have a blog showing how we are doing this and providing the entire documentation. But obviously, we have some more details to work out. Can you help me bring back the slides here? Where are they? No, I have them here. There we go. Okay. So hardware accidents aside, we can see details of what the cluster looks like. All right, so the hardware we chose is the global scale espresso bin V5. The aim was to build a cluster with 8 nodes and all SSD storage and spend less than $1,000 to do so. And we hit the dollar limit. We obviously didn't hit the reliability limit yet, but the problem is not with the hardware, so we should be able to do that reasonably soon. The system has SATA ports, which is why we chose it. It seems like a good way to do storage. It also has on-board PCI, which would be another option for storage that we're not using right now. We're just using SATA SSDs. And with the aim to hit the $1,000 mark or to stay below it, we chose the Intel SSD 545 because it's not the newest of SSDs, and so we can get them for extremely cheap. We can get the boards for about $49 and the SSDs for about $69. And so we're around $800 for an 8-node cluster. And then we're doing slightly fancier things like having a unified power supply so that we reduce the amount of cabling and just try to make it look nice. But those are frills. The cluster proper is $800. We are using the components that I described before. We're using kernel 419. That's kind of the default part. I don't know how familiar you are with embedded development. If you are, you know that the problem with these embedded boards is that they're very far from data center hardware. It's a completely different world. So for getting a reliable Linux distribution on embedded hardware, you have to have all the drivers. The most popular distribution for doing this right now is called Armbian, but the Armbian images for Espresso Bin V5 are not perfect, and we introduced a few more problems ourselves with our rebuild. So the pesky details need to be worked out. But once we get the Kubernetes part running, the rest seems to be seamless. We just need to manage to keep the cluster up for more than 12 hours. So the part is OS reliability, not Kubernetes problems.
Okay, quickly, trying to wrap this up.
And we do have one of the boards here if you want to take a look at the end.
So a little bit about the future of Rook. So we just released 1.0 last week. We are down to 1.01 at the moment. But I wanted to highlight some of the things we're going to work on for the next months. So 1.1 and 1.2 coming. So one of the biggest features we are trying to implement at this point is the external functionality. So meaning that not everything is actually greenfield, so you have brownfield environments too. So if you have an existing Ceph cluster, then you can actually bootstrap Rook in Kubernetes and then tell it to connect to this existing storage cluster. And then the only thing we'll be doing here is that we won't be managing Ceph's lifecycle, but we will only bootstrap resources that we can consume via CRDs, such as the file system, the Rados gateway, and the NFS file system. So that's the idea. And this is actually one of the first steps to actually achieve a takeover of an existing cluster. So the ultimate goal for that is basically to be able to, you have an existing Ceph cluster that is not containerized and that is not part of the Kubernetes cluster. And the goal here is just to take over all of these resources and then have them being managed by Rook. That's in the future. But still, we're working toward that goal. We also want to integrate with Maltus. I believe there is not so many things to do, but at the moment, if you want to get a better performance out of your cluster, you have to use host networking, which obviously brings more performance, but then also more security concerns as well, because once you do this, you basically expose all the network stack of the host inside your container. So in terms of security, that's basically not ideal. And what we want to do is to use Maltus to basically specify which interface we would like to use for our storage cluster, which will bring us more control and basically more isolation and more security. Dynamic volume provisioning on cloud provider is actually something I wouldn't think was that popular, but we have been getting many more requests on that, because actually there are a lot of people that are not only running terminal machines, but also on cloud providers too. So the use case here is that previously when I mentioned that you could specify which storage devices you want to use for your cluster, then here, for example, if you run on Amazon, then you'll be able to specify I want this amount of EBS volumes, and then with this particular size, and then we will just take care of the creation and the attachment of these volumes to virtual machines. And once we deploy Rook and Ceph, we will consume that. So you will not have to basically manually create volumes and attach them. That's basically, again, enhancing the user experience. Last but not least, bucket dynamic provisioning is one of the most desired features, and it's something that we're actively pushing into the community, the Kubernetes community. It's actually really equivalent to what we do currently with volumes, but at the REST object layer. So not only you can, because at the moment, you can only request the gateway, but the users don't care about the gateway, but what they care about is basically the bucket and the credentials. So the ultimate goal here is to claim a bucket and then simply consume it. So you just ask for a bucket, you get one, you get your credentials, and then you can start working. You don't have to do anything, you don't have to know anything about Rails gateway and stuff. The only thing you have to do basically is just ask for that bucket. So that's one of the things we're working on. There is a PR for that. I'm not sure if Jeff or John are in the room, but they're actually working on this. And yeah, that's super nice. One more thing really quickly. Last but not least, again, I'm super happy to announce that we actually got Rook into the Operator Hub. The Operator Hub is a centralized place that actually provides operators from the community. So if you're familiar with OLM, it's an operator concept that is basically an operator lifecycle manager that you can bootstrap in Kubernetes, and then you can inject CSVs to it, and then you will be able to it will be able to bootstrap your operator for you. So yeah, we're super excited to announce that this week. I guess, yeah, so many people helped us throughout this presentation, especially the people in Westfield, I guess, that helped building the cluster. So we would like to big shout out to them. And yeah, I'm just going to switch slides. So thanks very much for your kind attention. We were supposed to have more time, and we don't. If we don't have time for Q&A, that's not a problem. We'll be outside. Otherwise, we will be more than happy to take questions.